and let's start with Alberto's talk on the topological twisted indices. Thank you. And thank you for the invitation in this wonderful place. Today I want to talk about this object, the topological twisted index in various dimensions. Let me tell you what it is and why, and the angle that I will give to this talk, which is mostly toward holography. As you know, this is a very long story. Using a topological twist, you can put many supersymmetric theories, if you have enough supersymmetry, on almost all manifold in 2 and 4 dimensions. This goes back to it almost 30 years ago. And the topologically twisted index is just a sort of index in this particular theory with a topological twist, so it's just a trace of -1 to the f times e to the minus beta times the Hamiltonian of this twisted theory. So it's just an index. It's not the same as a superconformal index. It's not the same in general of the Witten index. It depends. So, but the structure is the same. It is an index in the sense that massive modes does not contribute because for each boson there is a fermion, and essentially this is protected under renormalization group, under favorable conditions. And the point is that these objects in various dimensions, here the important point is that there is always a circle here, can be computed using localization. So if you do nothing, so you just take a theory and you twist it, you get a number, 5, 10, 25, essentially. In the case where this reduces here to a Witten index, the number of Gauss states, countercats and signs. But you can also introduce, and I will be telling you how, in the moment, fugacities and extra stuff, in particular magnetic fluxes, for the flavor symmetries. So you get a non-trivial function of these background fields. And this non-trivial function can be used for many different purposes. For example, testing dualities, and this point is exactly on the same footing as the superconformal index, many other things that you can use as dualities. And from the point of view that I'm taking today, this index can be used to count states, and in some cases I will show you it's been successfully, this counting has been successfully compared with the entropy of a class of EDS black. And indeed I want to discuss these objects here going from 3 to 5 dimensions, 3, 4, and 5, with a view to holography. And let me tell you also, before starting with the details, what is
the dimension you're counting is in the holographic side or in the gauge?
No, in the gauge theory side. 3-dimensional gauge theory, 4-dimensional gauge theory, or 5-dimensional. Okay, so the view toward holography is the following. There are many interesting solutions in string theory and so on that interpolate between ADS vacua of different dimensions. The prototype example was studied by Mandelstam and Nunez more than 15 years ago. And this object you can interpret in various different ways. So, for example, suppose that you have a solution interpolating between ADS d+1 and ADS 2 times some compact manifold. Since here you have an ADS2, and we know that the horizon of supersymmetric black hole has an ADS2 factor, you can think of this as an extremal black hole in ADS d+1. Or similarly, there is another configuration where you have, if you want in the infrared, an ADS3 times a compact manifold. Whenever you see ADS3, you will think in terms of bounded conformal field theory, and I will discuss in a moment. But you can also think as this domain wall as a sort of supersymmetric black string. There is an extra dimension here. It's not just times plus the radial coordinate, but it's a string plus the radial coordinate here. So you can interpret these flows as black objects in various dimensions, or using holography as a renormalization group flow. So in the first case, you have a conformal field theory in D dimension. You put it on a compact manifold, and it flows in the infrared to a super-conformal quantum mechanic, you should expect. At certain point, with some limit, some exact of approximate super-conformalcy. And in this case, since you have an ADS3, situation is similar. You have a conformal field theory, you put it on a conformal manifold, it flows in the infrared to a conformal field theory. Now, the important point is that if you look at the supergravity solution, you immediately discover that in most of the solutions that are known, the conformal field theory is actually topologically twisted along N. This was one of the points of Mandelstam and Nunez. And in this case, you can use the object that I defined in the previous transparencies to get information about the flow, about holography, and if you interpret the object as black object, about entropy of black hole which are asymptotically ADS. So we'll come back to various examples in various dimensions of this game. The talk is based on a series of papers. There is a more general, the most recent one is about 5 dimensions. There are older one, and there is a list of other related things. There's a couple of years that I'm playing with these objects. Okay, so let me start with part 1, which is 3 dimensions. Just to fix the notation of 3 dimensions is particularly simple. Even for the point of view of field theory. So let's start just to the basic of field theory, the topological twist. So consider, for example, a 3-dimensional supersymmetric theory with n equal to 2 supersymmetry and put it on S2 times S1. So I'm taking the compact manifold I was referring to before, this S2 here. You can easily replace with any Riemann surface of genus G. There is just some very minor technical complication, but just to write simple formula, I will discuss S2. And the point of one way of seeing the topological twist is the following. On S2, you can turn on a non-trivial background for their symmetry, so that this background field for the symmetry can be chosen to cancel precisely the spin connection here. So the killing equation that you need to solve in order to put the theory on a curved space just reduce to the standard derivative of the spin equal to 0. So you can solve this equation on any manifold. And this is a way of reformulating the topological twist. You transform, in the Witten language, you transform a spinor into a scalar by changing the spin. You can change the spin by adding a background field for some symmetry that you have. So the important point is that on the sphere, you have a non-trivial background for their symmetry, so the integral of the curvature in suitable normalization. I'm not very careful with pi's and other things in the slides. The integral of this curvature on the sphere should be roughly 1, where 1 means that you need to choose the right coefficient in order to cancel the spin connection.
One of the two polarizations of the epsilon would now.
Yes, only one. Reduce on S2, only one chirality will survive. Yes. So the topological twisted index that I want to discuss is simply the partition function on the supersymmetric partition function of this theorem as 2 times S1. As usual, since you have an S1, you can write as a trace. Since it's supersymmetric, you will need to insert -1 to the f. And then the ingredients are simply the exponential of the Hamiltonian, but as usual, this is an index, so all massive states cancel, and this object is actually independent of beta, to put it just to be complete. And if you have other things, in particular global symmetry, you can introduce, for example, holonomies along S1, so Wilson line, you couple to the associated current, and you get background parameters from the Wilson line and other things. So this is essentially the definition of the object I want to discuss. I will be brief, I'm pretty sure that all of you have heard about localization. So essentially the point is that the localization allows to compute exact quantity in supersymmetric field theory. Every time you have a conserved charge that's square to 0 or some global symmetry, you can add a term to the action in such a way the path integral is independent of t, because this is the q of something, so then you can take it very large, and you can reduce the class, so a semi-classical approximation. So obviously you need to find a good deformation, a good theory on a compact space in order that the set of classical solution is under control, and you need to compute the one-loop determinant. It's a very old idea that's become concrete in the last 10 years with computation of partition functional spheres and other manifolds supporting supersymmetry. Now, I'm not, in this talk, I have no time to discuss the technical detail about all these localization computations, so I will give you the final result for each of these. And as you know, looking at other example, the basic point is that whenever this trick works, it reduces the full path integral to some sort of matrix model. So you have a set of variables that remains, like eigenvalues in the matrix model, continuous. Sometimes you have topological sector you have to sum over instantons in original Western computation. Here we will have monopoles and other things. But the basic story is that at the end of the story, localization always reduces the path integral to some integral over a certain set of variables. I'll tell you what variable we need in this case in a moment, and possibly a sum over a topological sector, and I'll tell you what we need here. In this particular case, the localization, if you look at the structure of the vector multiplet, n equal to 2 vector multiplet in 3 dimensions, it contains a vector field, contains a real scalar, fermions, and an auxiliary fields. So essentially, localization tells you that the BBS locus is given by specifying an arbitrary value for sigma, so the scalar can have an arbitrary value. Since you have an S1, it's natural to expect that also the Wilson line, the expectation value of A nu along the S1 can have an arbitrary value, and in this is the case. So these two guys, AT and sigma, can have an arbitrary value. It's convenient to put them together in a complex number because the final result will be holomorphic in this combination of Wilson line and sigma. And these are the integration variables, so you integrate over these guys. And then, as I was mentioning before, you have a topological sector. You have a sphere, so the gauge bundle can be non-trivial on the sphere, and indeed this is a part of the localization locus. So for each magnetic flux, gauge magnetic flux, you have a different sector, and you have to sum over all the sector, and this function will also depend on the gauge magnetic fluxes. And then, as usual in supersymmetry, you need to specify where you have to integrate, so you need a contour of integration. So here I'll just show you the result, just to show you the typical ingredients. So you have to make an integral over variable u, and it's convenient to exponentiate this u in order to get a variable x that allows to write everything in rational form. So x is just exponential of this u. And the ingredients is that the integral, as usual, is a part contains a classical contribution, a one-loop contribution, and the guys are simple. So essentially the classical contribution, you get it only if you have Chern-Simons term in your theory. And is of this form. K is the Chern-Simons value. It couples to the magnetic flux, and there is this x here. So this is the classical case. Then you have the one-loop determinant. The one-loop determinant for gauge boson just produces something which is just a sort of van der Waals determinant. So very simple, natural to expect. And each chiral multiplet produces a function. This is the important piece of the story, which is a rational function of this variable x, or is just the weight of the fields in a given representation to some power. And the power is specified by the value of the magnetic gauge flux. There is a factor of 1, and there is also a dependence on the R charge of the field, because I used R charge in order to twist the field. So it's this rational function to some power. You multiply these guys here, you do an integration over a specific contour. The specific contour is a long story, it's specified by supersymmetry, so it comes out of computation. It's not the natural one, so when you see a matrix model with a Mandelstam, you would like to, I don't know, integrate over the unit circle. It's not exactly like that. you need to use a particular prescription that has appeared many times in localization now, that is called taking the Jeffrey Kirwan residues. I will not need it in this talk. If briefly, I can tell you that essentially it tells you to take the poles of this integrand corresponding to somehow, suppose that you have a U1 gauge theory, you just select the poles that come from the fields with positive charge on the U1 and not the negative one. But there is a pretty cool mathematical way of incorporating all this stuff. And it's actually non-trivial how it comes out from computation. And let me mention that you find similar structure in at least two other computations that are the computation for the elliptic genus in two dimensions using localization, and the computation for quantum mechanics in one dimension using localization. You get exactly the same structure. Okay, so this is the picture. I will come back to the example that I need later. And now let me move to the black hole part of the story, the holographic part. So this was a gauge theory in three dimensions, so holography now is ADS4. And the interesting object are ADS4 static black hole. So you have a matrix of this form. You find many solutions of Einstein-Maxwell equation. And what you can do in 4 dimensions is to introduce electric and magnetic charges, both of them. So you can have family of dionic black hole. And again, there is a class of black hole, in particular the static one, no rotation. These are peculiar to 4 dimensions, that preserve supersymmetry precisely with a twist. So if you look at how supersymmetry is preserved, you find again this equation. Now AR is just one of the fields in the bulk, and it's turned on. It's turned on in such a way that you cancel the spin connection, so you reduce this equation to the simplest derivative of epsilon equals 0, which is again solved by epsilon equals 0. If you go to the boundary, the structure remains, and you discover that the dual of this theory preserves supersymmetry with a twist, essentially. So you're turning on this field as a background in field theory also. So this is precisely the dual of what I was mentioning before. As a solution, you can interpret it as a domain wall. So there is a boundary. In this picture, I took some sort of Euclidean continuation. So my boundary is an S2 and a Euclidean time that I compactify on a small circle. And so the metric for large value of the radial coordinate is essentially ADS4. And then when you go to the infrared, in the language of organizational group flow, you will find an horizon where you find an ADS2 and the 2 sphere. And clearly it's easy to adjust this function in such a way that you interpolate between these 2 configurations. In the infrared, you just need that the function in front of the sphere get a constant value, and the other function gets the right pole, the second order pole here. Okay? So this is how you interpret as a renormalization group flow. You go from ADS4 to ADS2. These are the 2 ways of looking at the same object, the black hole. And from the point of view of the dual field theory, so there is an S2 everywhere. So your theory is compactified on S2. If you go to a Euclidean, the time becomes a circle. So indeed you get S2 times S1, is what you are doing. And the point is that all these magnetic charges here survive near the boundary, so they correspond to some deformation of your theory. In particular, they are performing this topological twist. So you get an Hamiltonian of a topologically twisted theory on S2. And if you want, you can even reduce on S2 and get a quantum mechanics. You just take all the Caruso-Klein mode on S2. This quantum mechanics will have many Landau levels, so it's a complicated object, but it's nature of what it is. You put background fluxes for asymmetry and possibly for other fluorosymmetry, you get Landau levels, and you get a complicated quantum mechanics. And what I was computing before, if you compute this topological twisted index, you can rewrite as this trace, as this precisely as before. And this trace here, now from the point of view of quantum mechanics, is really a Witten index. You have a quantum mechanics, is the Witten index of the quantum mechanics that you get upon dimensional reduction. Oh, notice that in this game, the black hole is dionic, so it has magnetic and electric charges. The magnetic charges are hidden here, so are in the Hamiltonian, they give the Landau levels. So for each set of magnetic charges, you have a different index. The electric charges are not manifest in the index, but these guys here, delta, is a chemical potential for some global symmetry in your theory. So this chemical potential is just the chemical potential canonically conjugated to the electric charge. So the electric charge enters through chemical potential. So essentially you are in a grand canonical picture for the electric charge. So this is counting states, and if you have to compare with the entropy of the black hole, well, these are the set of ground states written in grand canonical ensemble. Well, what you expect is the entropy is just the Legendre transform of this object. You go from grand canonical to microcanonical, canonical, where zero temperature. So I don't know what I should use, probably microcanonical. You just take a Legendre transform with respect to delta, you compute the electric charge, and you expect that this guy, this object here, is the entropy of your black hole, at least in some thermodynamical limits, because this is statistical mechanics. So it will work when all your charges are big enough. And as we are doing holography, all the charging will be, in some units, are order n to some power, so they are big enough to, if you want to match with the holographic computation, you always are in the limit where the charges are.
And that I is there?
What?
That I is present in that?
Which?
I mean in the last Legendre transform formula.
Yes.
So it is log z minus I times delta times q? Or?
Oh yes, there is an I because, yes, it's complexify chemical potential, okay? But you see the I comes from here. The final result will be real, okay?
Do you expect some kind of conformal invariance on the horizon?
Oh, okay. Good question. I don't know. I would expect because there is no relation group flow,
Yeah.
but cannot tell you much more. When I expect yes. I don't know what kind of superconformal quantum mechanic is this. So, for example, in the business of asymptotically flat black hole, this N has this picture, a similar picture, but same picture is, if I understand correctly, is a quantum mechanics where there is a set of ground states, and then again, and the entropy set of ground states. So I cannot tell you what's going on here. I can do the computation of this index, which is a regularized index, and show that it corresponds to the entropy. But at the moment, I have no real way of identify this quantum mechanics in a different way. I know that it's a compactification, but with infinite many modes, and more than that, in the computation that I'm doing, I'm summing over topological sector. So in each sector, I can tell you what are the relevant modes. But then the partition function is a sum over all the sector, and the result is something very complicated. But yes, there should be some quantum mechanics, but I cannot tell you precisely what it is and what properties the quantum mechanic has. So there is an interesting example where you can test this game, because there is a family of ionic black hole in ADS 4 times S7. They have electric and magnetic charges under the isometry of S7. So you have 4 possible Descartes subgroup of SO8. And for ADS 4 times S7, we know very well that dual field theory is a BJM. So there are 2 gauge groups written in n equal to 2 notation. There are 2 gauge groups, Chern-Simons level, opposite Chern-Simons level, and 4 chiral bifundamental fields with a superpotential. So we know everything about the gravity side and the field theory side, and then you can try to evaluate this topological twisted index. I'm not discussing the detail because even the evaluation of this is complicated, so I'm going to give you some general properties. So this is the guy that you need. Using the rules that I told you before, you need to do a sum over topological sector. You have 2 gauge groups, so you have a sphere, you can put a magnetic flux for UN here and another for the second UN. So you have this sum over two vectors in Zn, m and tilde, which are the magnetic fluxes. Then you have two gauge groups. You integrate over Cartan values variable for each of the gauge groups. So say that x refer to this guy and x tilde refer to this one. Then you put the classical action, which is Chern-Simons only. You put the van der Waals for both gauge group. And this guy here are essentially four guys that are the contribution of the four chiral fields that you have. You see that they have this form here, rational functions. The dependence of the gauge variable is, say, xi over x tilde j, is telling you that you have a bifundamental field, positively charged under the first group and negatively charged under the second. There is an exponent that depends on the gauge fluxes, and there are also background fields here that are written here. So this y, y1, y2, y3, and y4 are essentially the exponential of the chemical potential I introduced before, and you see that they enter in a simple way. In this parameterization, I choose to attach one chemical potential to each field, y1, y2, y3, and y4. Then, since the superpotential should be invariant under any global symmetry, this means that these guys are not independent, but the product is 1, so its product is trivial. So these are the chemical potential, complexified chemical potential. And there are also these guys here, which are the magnetic fluxes. The magnetic fluxes of the black hole appear as this parameter, P1, P2, P3, and P4. They also satisfy a constraint, written in this notation is the sum should be 2. And this constraint, if you look at the details, is interpreted as the twisting condition. So you need that the arc symmetry should have a particular value. This translating this sum equal to 2. Or if you prefer, if you want to assign integer to these guys, this integer here looks like arc symmetries, and their symmetries of the superpotential should be 2. Okay? There are various ways of looking at the same problem. Now, the fortunate thing is that you can solve this matrix model in the large L limit. It's actually non-trivial. I have no time to explain the detail, but what you discover is that let me make a comment. Some of you may have argued that, okay, why this guy should be the entropy? There is -1 to def. This is not the number of ground states. It's the number of bosonic ground states minus the number of fermionic ground states. Well, the answer that I have is that I don't know how to compute the guy without the -1 to def. That would be then. So when we started the computation, we say, let's hope to be lucky. There are many situations in string theory where there is a similar index, and you're lucky enough in the sense that in the relevant limit, large charges, large n, there is no cancellation between ground state of different type. And what you discover from the computation is that this is the lucky case. There is no cancellation between bosonic and fermionic ground state. And indeed you discover that this object, the logarithm of this object, scales in a natural way for a three-dimensional theory. So if you look at the free energy of a DJM, you know that it scales like n to the 3 over 2. So it seems that all the degrees of freedom are captured by the index.
And what about the coefficient?
Oh, the coefficient is the correct one.
Yeah, but that's very lucky, no?
Well, otherwise I wouldn't.
No, I'm saying that it's not so ridiculous.
No, but if the coefficient is not the same, means that there is a cancellation large cancellation between boson and fermions at leading order and n. Okay.
I mean,
so being lucky means that the leading order
the
is
same situation, right?
No, I know. I'm saying I think it's very easy to argue that it will be going like n to 3/2. It will require a miracle otherwise. But yeah.
Or you will say
or
is n to the 3 over 2 would mean partial cancellation. Right?
Yeah.
I agree. I don't know if, well, in other cases where it doesn't work, there is a total cancellation. In the superconformal index, the start was with 1, not n squared.
But then there are reasons, yeah, but okay.
Okay. I'm a little biased because there are black holes where this game doesn't work. In that case, there is a very large cancellation. So I don't know. Well, but I agree. N to the 3 over 2 can mean no cancellation or partial cancellation.
If you include 1 over n corrections, then you do not expect the
That's an interesting story. For a symptotically flat black hole, there are examples where this story goes on to all order. I think Sen has an argument based on the on S2 actually. The rotation invariance on S2 that I cannot apply here. In those cases, you know that is the same at all order. There are examples where this argument doesn't apply, and people compute both the entropy and the index, and they do not match. They computed in field theory because in string, that's string theory. This is M theory. I wouldn't know how to compute the 1/n correction, but there are models, the modified where you can use string theory in order to compute all the states with or without supersymmetry. And they compute both what you would call the entropy and what you would call the index in string theory, and they match, but they are different. In this case, if I would like to apply the same argument, I would need to use instead of the rotation on S2, I would need to use the R symmetry inside SL2R. But I think it's probably not allowed because the representation theory of SL2R is not trivial, it's not compact. So I don't know. I could cook up for you a naive argument why it works. The R symmetry, or the ground state of the black hole should be superconformal invariance, it should have R equal to 0. I don't think this is a correct argument. So it's a naive one that might explain why it works. But I don't know at final term. And I even don't know exactly how you would test it because this is really, you need to do correction of the black hole in M theory, right? So it's stuff.
In the larger limit, is it still true that all the magnetic sectors contribute, or the sum is dominated by some sector?
No, I think all of them contribute. I'll show you how to do the computation in the next slide.
Because it looks roughly like something to the n times difference of m. So maybe I look at any given term, it looks like something to the n times m. So maybe something. It's only one term that's
so for sure it's not enough to choose the trivial one m equal to 0,
yeah.
and that's not
even at large.
Even at large.
But
so,
it's something to the power k.
No, but there's some n. Look at the terms below. Right? It's like n products, or what? Or the next one. Right? It's n of those guys. So it's like it looks something like
I think there are more than one contributes. Maybe not all of them, but a range of values of n contribute.
I think that without the contribution of magnetic fluxes, you would have got n squared. Because you've got field theory with n squared degrees of freedom. Must be magnetic fluxes that are cutting down n squared.
Yes.
No, that might be true, but I didn't say it was maybe the true one, but there's no way of isolating some part or even
let me show you next slide.
That would be important for quantum mechanics, right? If you could,
yes.
If we could do that, then we would have a quantum mechanical.
What are the not the flux? So the point is that these fluxes here only enter at exponent, okay, in a simple way, and then you have to take residues of these guys. And if you look exactly at the residue graphic here, one essentially tells you that it's always a lattice of fluxes that you have to sum over. So essentially, if you want, when m is too large or too small, the pole goes up, not down. So you just have a lattice. So you can just do geometric series resummation.
All those n's are just 1, 2, 3, 4. There's nothing to the power n.
Well, there's n terms, right?
Okay, but you can take the vacuum from any.
Yes, it's not completely obvious what you. I can have a look at what happens when if you choose one value and.
No, I understand it's complicated. The only reason I'm asking is that from quantum mechanics perspective, this is what makes the problem hard somehow, right?
Yeah, if you can identify one.
If you could identify some subset.
But able experiment is much more complicated than that. Then we would say, okay, I reduce in the sector. I know what is the set of zero modes. It's just I have the suspect that is more complicated than this.
Could I have a related question? Can it also be worked out in the limit n goes to infinity, k goes to infinity with n by k and fixed?
So the tooth limit, yes, you can do the tooth limit. You can even compute a small correction.
So for instance, now when you take the toph coupling to 0, then you see that it's n squared.
I think, well, it's a story, yeah, because in that case, that's the usual story, and n to the 3/2 square root of k you write as n squared.
Yeah.
That's a strong lambda. At large lambda it would be n squared
I
minus
want to
square
set
root.
the two.
But I would not take lambda to 0.
No, sorry. Lambda to 0.
I would expect that to get a free field answer, so n squared.
Lambda to 0, I'm not sure. So I think you need to take, no, the thing that I can do is to take lambda large and do a perturbative expansion in power over 1 over lambda, which is not what you want.
Not whatever. That's the limit in which you could restrict to only 0 magnetic fluxes. Because that's the limit where k goes to infinity.
Yeah, then it fixes
So it should be pretty easy to do because it's just one set there.
Yeah, that's right. That's right. The case is clear. What I can do is perturbation in 1 over lambda.
Yeah. And the fact that there are n squared degrees of freedom will automatically give you an answer n squared there, presumably. Right?
Presumably, yeah. Let me flash this because...
Sorry, so just to ask one more question related to this. So maybe the way to think about it is that in the quantum mechanics is sum over m is enforced on gauge constraint, the quantum mechanics or something, right? It's reducing, right?
I think so. I would expect that quantum mechanics is...
You have many copies of the same system and then you have to sum over them to get something gauge by.
I think something there.
So let me show this because I will need a similar picture later. If you sum m, essentially, you get rid of the magnetic fluxes, you get an integral to do, you will get a, when you sum a complicated denominator, essentially what you have to do is to take all the poles of this denominator and you use residue theorem, so you can always write this as a sum of all the possible zeros, poles of the denominator. Turns out that this poses a physical interpretation, because if you take the three-dimensional theory and you consider as a compatified -1 with all the Kaluza-Klein modes, you can write essentially a twisted superpotential for this two-dimensional theory, which is roughly a coefficient of this form. And it turns out that the zeros of the residue that we have to take have the physical interpretation as the critical point of this superpotential. So these are the so-called Bethe-Vacuum that also enter in the gauge, what's the name, the Nekrasov-Shutterbill story of integrability, gauge slash duality between gauge integrability and well, it definitely is the integrability story of this two-dimensional theory. So, and then the important point is that, so DEM is gone, so I don't know exactly how to answer your question because the way I do the computation, DEM has been eliminated, so it's a sort of constraint. But the point is that when you write in this way, you have a sum of terms, each of these terms is big, so essentially in the algebra what you expect is that there's just one vacuum of this set of equations in two dimensions, one Bethe vacuum that dominates the partition function. This is indeed what happens. So, without entering details, because it will take too long, the point is that you can write this Bethe equation, you can formulate the larger limit, you can solve it, standard, well, not really standard method, but you use a resolvent, and so on. And you find that at the end of this computation, that after many subtleties, that the final result is very simple. Because this is the final result for what you would like to compute, the entropy is the log of z minus this term, and you have to take the Lagrange transform. This is the object that you were trying to compute, and this object here is essentially simple because it's linear in the magnetic charges, and it's the simple derivative of a function, which is not so ugly because it is n to the 3 over 2, which is what you expect, and essentially the square root of the product of all mechanical potential. So these ugly bits are then reduced to something very simple. And this called W because it's precisely this function. So you find the critical point, you plug it back, you get a simple function, which is this. And then there is a simple way of seeing that the log of z can be, well, not a simple way. There's a way of seeing that the log of z can be written in this way. You evaluate this, you open the literature, you look at the entropy of the black hole. The entropy of the black hole is an ugly beast. In the case where all the charges are equal and no electric charges is already the square root, polynomial square root of other things. So don't expect the usual square root of Q1, Q5 times n of Strominger and Waffa is already complicated when you just have one parameter. and it's very ugly when you have all the 6 of them. But you can check that this is precisely the entry of the black hole. And you can also do an independent check because using supergravity, because supergravity knows how to compute the entropy using the so-called attractor mechanism. So they just write a set of BPS equations. And the attractor mechanism is precisely this equation. It's exactly the same equation because in the language of gauge supergravity, this function here is just the prepotential of the relevant and equal to gauge supergravity. So you can check one for all that this works. And indeed, this function is curious because it can be interpreted in many different ways. It's the prepotential of the gauge supergravity that describes the black hole. And it's also, by a sort of coincidence, a function that you find in the literature, if you compute the free energy on a string, something completely different, as a function of the triangular symmetry. This was done by Lebanov, Pufu, collaborators. You find precisely the same function here. Okay, so it works. It works very well, and it's been generalized to various other situations. There is some sort of universal black hole that you can always have in all compactification of n theory type 2A. You can do the formation, you can do the massive type 2A. So there are many models where you can do the same computation with three-dimensional theory and test with gravity.
Did the contour of integration play any role in your calculation? Was it
no. It's just selecting a flat is, no, it's not. In the larger limit,
it's just a saddle point
Yes,
analysis.
yes. Usually, typically, the certainly with contour of integration in the larger limit, luckily enough that it goes out.
So sorry, then when you match to this calculation by Klebanov and friends, so f extremization is the thing that's matching to when they find the trial R.
So this is the this is the guy before extremization.
Before extremization.
If you extremize to get the free.
But that equation is the equation for the extremum, right? That's what
but it's not the same extremum. So they took the derivative of this and they set to 0, and you get that's the one that the derivative before, which are they are charges of ABJM. So you get 1/2, 1/2, 1/2, 1/2.
Yeah.
Okay. Instead, I'm taking this function. I take the derivative, multiply the fluxes, I subtract other things, and I extremize this, and I get something different and non trivial. It's not the same extremization. Only the functional form of the function is. So let me go to 4 dimension. So in 4 dimension, you can consider something similar. This time I want to take S2, but instead of S1, I put a T2 here. So what I'm computing is well known in conformal field theory. So if you call Q the usual exponential of the modular parameter of the torus, L0 is the conformal field theory L0, and you put chemical potential for the various charges. You're essentially computing an elliptic genus this time, not a Witten index, but it's the correct object to compute for a conformal field theory. And from the point of view of localization, you get what you would expect. So if you take the S1 case, you go to a T2, you expect some elliptic generalization. So the rational function that I was discussing before becomes a bunch of theta function. Okay? This replaces the rational function. The exponent is the same. So it's an elliptic generalization of the previous example. Holography. This time I want to, this strongly suggests a conformal field theory. So I want to flow to, not to a quantum mechanics, but to a conformal field theory too. So I can take solutions that interpolates between ADS5, the conformal field theory in 4 dimensions, and ADS3 times S2. So this is a flow from a conformal field theory 4 to a conformal field theory 2. Again, there are examples in the literature. There are plenty of examples. In particular, this guy, Benini and Bob, have a series of papers that studied twisted compactification of n=4 superior means. So the solutions are asymptotic to ADS5 times S5. And what they did essentially was to say, okay, I compactify my conformal field theory on a sphere, 4-dimensional conformal field theory, I will get a 2-dimensional conformal field theory. Let's compute the central charge using field theory. Let's compare with the gravity result, and they match. Okay? So this is what they did. With this game, you can compute a little more than the conformal field theory. You can compute the full elliptic genus. Okay? So Again, the matrix model is similar. The rational function has been replaced by theta function. The Vandermonde has been replaced by a theta function version of the Vandermonde. And this time, however, the lateral limit is too hard. I don't know how to do that. There are theta functions, and the trick that I used before doesn't work anymore. But there is another interesting limit that I can take. Since now I have a torus, I can take the modular. I can play with the modular parameter of the torus. So I can study the, let's call it the high temperature limit. It's not really temperature, because supersymmetry we are at 0 temperature, but I take the modular parameter to 0, let's call it the high temperature limit, and what I should expect, this is an elliptic genus, I should expect a kind of behavior. And what you can do is to evaluate this in the saddle point approximation. See, the method is similar in the high temperature limit, and what you indeed discover is that the log of z behaves as 1 over beta, where beta is this fictitious temperature, and the numerator is precisely the conformal field, the central charge of the two-dimensional conformal field theory. It's not only the central charge, the real central charge, but if you introduce chemical potential as before, you precisely get the trial central charge, the object that you typically define depending on asymmetry, and you extremize to get the right figure. So you get a Cardi behavior in this case, which is what you expect. And Cardi leads to you see Cardi, you think of black hole. Well, there's an obvious way of getting a black hole out of a black string. Take the black string, is this Strominger-Vafa, compatify on a circle, add the momentum along the circle, you will get in a black hole in one dimension less. Now, if you want to match the entropy, it's easy. Then now it's really Cardi argument. So the momentum is canonically conjugate to the temperature. You do a Legendre transform with respect to the temperature. This is Cardi argument. And you get that the Legendre transform of this gives you the square root of n times the central charge. So the Cardi formula. And this is just the formula that tells you how many states there are in the given conformal field theory at energy n. Is square root of n times the central charge. And if you compare with gravity, you will discover that as we've done even before our computation, you can do in general. If you start with a black string, you dimensionally reduce, you will get the Cardi formula. So everything works pretty nice.
So here as well, there's a sum over magnetic sector. So it's also
there is one, which is not the trivial one.
Yes.
You resum it, and there is a bit.
So it's also a bit confusing to think of it from a CFT to.
Oh, the CFT again. I think it would be. People are thinking, what is this CFT since long? Okay,
Yeah.
these guys sometimes one of them tell me, finally we got something. Maybe we have. Because at the point that yes, CFT. It would be nice to write as I don't know,
right.
maybe not minimal model, but something and compare. Same problem. It's a sum of a magnetic flux. I don't know. It would be very nice to have an explicit example where you have.
So you can understand what that
but
means.
I expect there's a sort of duality. It will not be written in the original degrees of freedom. It would be something different, and you need to figure out what it is. But even here, it's not clear.
Yeah,
I don't know of any single example where you can figure out what is this.
Well, we know CFT2s that are holographic, and they all have some singlet constraints. Something it would be nice to understand whether that's connected.
Okay, just a quick comment. Here, essentially, I was setting all the parameters to the canonical value, but there are also chemical potentials. So in principle, you can construct. They are not read in the literature. You should do it yourself, but I expect they exist. You take this black string, you compatify, you can add electric charges, you will get a black hole. You need to write the explicit form of the black hole. So the prediction for the entropy is this one. You take the Legendre transform, and you get a structure like this. What is interesting when you get this structure is that everything depends in a very simple way on the property of the gauge theory. The Tufte anomaly coefficient enter in the matrix. These are the electric charges. And you can check easily that this result matches with the expectation of gravity, the Tractor mechanism. And it's also interesting that if you just use the elliptic modular property of the elliptic genus, you discover that you can predict by looking at the elliptic genus that the number of states of electric charge should behave precisely in this way. So everything is consistent with field theory expectation, even with the elliptic property of the elliptic genus. So in the last 10 minutes, let me go to 5 dimensions. where the story, obviously, if you increase dimension, the story becomes a little bit more complicated. 5D is just, I can tell you just the first part of the story. We have done something, but the point is that now we are in 5D. You take a 4 manifold, you take a circle, just take M4 as a Keller manifold, so you can use the Witten trick, so you do sort of n=1 twisting, you can do on any Keller manifold. So it's a topological twist. But the point is, now you have 4 manifold, so you can have topological sets that are instantons, and typically you have. So things are complicated by instantons. When the manifold, so we found this way of dealing, this preliminary way of dealing with this problem. In the case where this is a toric variety, you can, so there is a T2 action on it, you can introduce equivariant parameters. So you can put the theorem on omega, the form background. This is what Mandelstam did. And you can study the problem with equivariant parameters. You would say it's more difficult than without, but it turns out that no, because luckily there is for an analogous case in 4D, for the analogous case without the circle, because of long time ago had a conjecture for the structure of this partition function. It's saying, okay, it's not difficult if you have a toric manifold. Toric manifold, remember, you can obtain toric manifold by gluing copies of C2. So typically you draw a toric diagram. This is for P2, and the toric diagram essentially tells you that this cone here is a copy of C2. This is another copy of C2. This is another copy of C2. You glue it together, pretty much like you make the sphere by gluing the north charge with the south charge. And this vector tells you how you have to glue it. So you can obtain P2 by gluing copies of flat space. So the conjecture was, okay, let's take my, Necker's conjecture is, take my partition function, Necker's partition function, in the equivariant background, take various copies of this for each copy of C2 that you have, and glue them together. And the gluing is essentially works in this way. You have to define for each copy of C2 a different set of parameter epsilon. So these are the standard one, epsilon 1, epsilon 2. In the second copy, you put some linear combination. There is a rule for doing that. You also shift the gauge variable by some integer that play the role of the magnetic fluxes. So in this game, the magnetic fluxes are associated to all these vectors in the fund. So you have many numbers P that play precisely the role of the previous magnetic charges, and they are associated to the toric data. And you do this gluing, you integrate over A, and this is the conjecture for the partition function on M4 times S1 when epsilon 1 and epsilon 2 are different from 0. Where again, this guy A, now I call it A, is the same guy as before. There's a Wilson line on S1, and there is a real scalar that you can introduce in this 5-dimensional gauge theory. You combine in a homomorphic variable A. Now, this is the case where epsilon 1 and epsilon 2 are different from 0. Maybe you remember that the Necker's partition function is singular when epsilon 1 and epsilon 2 goes to 0. It's actually a double pole, and the coefficient is the Seiberg-Witten potential. But it turns out that when you glue, the various singularity cancel together, so everything is smooth, also in the limit where epsilon 1 and epsilon 2 goes to 0. And if you take this limit, you get still a mess. But if you are interested in holography, you may use the usual argument. Instantons that has the powers of n should not be relevant. So if you forget about instantons, you just have the classical and perturbative part of the Necker's partition function. You can explicitly take this limit, and you get something of this form, which is not too different from the example that I had before. So you have to sum over magnetic fluxes, you have to integrate, you have an integrand, and you see that the building blocks are the same as before. This rational function is precisely the same that was in 3 dimensions. The only difference are the exponent. There is a reason for that, why you get this guy here every time. Essentially because this is the basic building block of any quantum mechanics. So if you do localization in quantum mechanics, you will get this guy here. This guy here is 1 minus x to, suppose for E1 gauge group and a field of charge 1, this guy is square root of x divided 1 minus x, or 1 minus x divided square root of x. Forget the square root of x, it's just overall charge. The difference is, according to where this is positive or negative, is 1 minus x and 1 over 1 minus x. Well, expand 1 over 1 minus x in geometric series, 1 plus x squared, is the contribution of a bosonic field, okay? And instead, 1 minus x at numerator looks like a fermionic field. And indeed, in quantum mechanics, there are two multiplets that you can write. One is called chiral multiplet, contains bosons and fermions, and there's a partition function that is 1 over 1 minus x. And the other one is called the Fermi multiplet. It's curious, it only exists in quantum mechanics. It just has fermions and auxiliary fields. So its partition function is purely fermionic, 1 minus x. So you get these building blocks are precisely building blocks of quantum mechanics. And these numbers here are just multiplicities. So you have this theory in higher dimension, you compactify, you get 0 modes, and this number here can be computed typically using index theorem. You use the Riemann-Roch theorem, and for example, for P2, using the Riemann-Roch theorem, you will get a number like this, and you can check that these are precisely the number that come from this expansion. So this is the structure again. And in the very last few minutes, let me tell you a few things about the large and linear. This is again preliminary. So the basic problem is here. If I try to do the same trick I did before, I have exponent which is quadratic in fluxes. So I cannot use the geometric series trick. This is more like a theta function. Then there is a non-trivial contour of integration. I don't know exactly what call should I get. I haven't even shown that this contour is really a Jeffrey-Kirwan prescription, so there are many still missing ingredients. So the basic point is that I have no idea at the moment how to do a proper computation here. But if you make a sort of conjecture, if you remember in 3D, and in 3D was a computation, in 3D the partition function was written as a sum of residues, and all the residues has a physical interpretation. The critical point of the two-dimensional theory that you obtain by compactifying on S1. Okay? So here there is a natural object to consider, not a twisted superpotential, because if you compactify from 5 to 4, you are in 4 dimensions, but in 4 dimensions there is something very obviously related to this kind of object, is the Cyber-Witten prepotential. So if you write the Cyber-Witten prepotential of four-dimensional theory, this is a formula that has been written by makers of 20 years ago. If you sum over all the Kaluza-Klein modes, this is important, you keep all the Kaluza-Klein modes, the one-loop contribution of the matter field can be resummed to a polylog function. And this is the form of the Cyber-Witten prepotential as a function of this variable A. Oops, sorry, I'm going in the wrong direction. With all the Kaluza-Klein modes. So the natural conjecture is that this guy should have the critical point of this object should have something to do with the critical point of the matrix model. I don't know how to prove it, I don't even know if it is true, but what I know is that if you assume this, you get pretty nice results in various cases. Actually, the only case that we could really study is the case where the four manifold is S2 times S2, because the direct product, and you can do sort of first compactification on 1s2, you go to 3 dimension where you know how to do things. In this case, the structure of the matrix model is the same, it's quadratic, so it's still a complicated object. I don't know what to do. But the point is that if I see this guy as many copies of the 3-dimensional problem, so you have a sphere, you reduce on it, you get many copies of a 3-dimensional model. A becomes the gauge variable in 3 dimensions. The point is that since you compactify on 1s2, each of these S2 has a different flux, and then magnetic flux. So if you compactify on S2, you have, again, many sectors. So you get many 3-dimensional theory labeled by an integer. You have many of them. And what you do now? Each of these has a twisted superpotential of its own. This is a function of A and N. Well, the conjecture is that you have to extremize this, and this will give you a saddle point, say, for A. Okay? But then you have N, you have to sum over all N. What physics N? Well, our conjecture is that, okay, you also have to extremize the prepotential. If you extremize both of these, you have a well-defined saddle point. that you can plug in and get a result. So the result I'll show you very briefly in two cases, the cases that we look at. In 5 dimensions, there are two interesting. The simplest one are the theories that have an ultraviolet fixed point. For example, USPN and F flavor and antisymmetric was introduced by Cyber 20 years ago. It's claimed to have an ultraviolet fixed point in 5D. And what you can do is to compute the critical, the 7 points, so the extremum of these two quantities, evaluate these two quantities on the extremum, evaluate the index of the extremum, and if you evaluate the prepotential on the extremum, curiously you find again that this, as a function of the parameter, is equal to this time the partition function on S5. S5 has nothing to do with this problem. It was the same in 3 dimensions, it's the same here. This is a partition function of S5, was computed by Pufo Jafferis 5 years ago, and you find it up to a coefficient exactly the same expression. The behavior is then to the 5/2, which is the right behavior in 5 dimensions. And if you compute the index, you get essentially this time a second derivative of this guy here. Now, this guy here is what? The point is that these guys have a nice scaling, the right scaling with n, and you would like to compare with black hole. This time there are not so many black holes. In particular, there are no black holes with non-trivial magnetic charges. We are looking for them, but we need some time. Clearly, this expression here gives a prediction for a class of ADS black hole. So the dual of this theory is massive type 2A on ADS times S4. So if you find black holes that have this horizon topology, hopefully this is the formula that's computed for those guys. The second example that we look at is the maximally supersymmetric theory.
So when you say you have not found it, do you know the interpolating solution? Is that what you mean?
No, there is just one example, which is the so-called universal twist. So it's just a number. Unfortunately, I cannot test the dependence of charges. There is a prediction in the literature that seems to be wrong, because the gravity computation, there are missing factors, I think. There should be some paper in a couple of days by a Korean guy that claims that the solution is wrong. If I try to match, I get the right dependence. I have a mismatch with the coefficient. So coefficient can be normalization, can be other things, can be that my conjecture is wrong. There is another group, Willett, Jain, and Quicigno, that got the same matrix model and have a simpler conjecture, which is like yours, that at least for this universal twist, only the sector with 0 magnetic charge contributes. In this case, you get another number. At the moment, it matches with the one in the literature, but the one in the literature seems to be wrong. So there are clearly that. So it would be very nice to get the fact, normalization are easy to scrap. Sorry. The dependence of the magnetic charges is something trivial. So if you have the black hole as a function of the magnetic charge, then you can start saying something.
Yeah,
there is another case that works. Let me finish. Can I have 1 minute? Is 5-dimensional, n equal to super Yamese in 5 dimensions. And this time you do the same, and again you find the same analogy, same structure. The prepotential is the same as the free energy on S5. Here is written in terms of chemical potential. This was computed by Mina, Nedelin, and Zapzin again 5 years ago. And again, the log n has the same structure. You take a second derivative. So the structure is always consistent. It's very similar to 3D. In this case, I can do a more refined computation because this time n equal to the maximally supersymmetric theory in 5D. I think of it not a 5-dimensional theory at the point of view of conformal theory, but I consider it as a compactification of 2, 0 on a circle. There is this conjecture that tells you that 2, 0 on the circle is exactly maximally supersymmetric Yamese. So if you take this seriously, what I'm computing is something related to the 2, 0 theory on an extra circle. So I get a T2 here because I had to add a circle. So I'm supposed to compute this object, which is the elliptic genus of this conformal field theory, defined on S2 times S2. Again, there is a twisted compactification. this theory in 6 dimensions is compatible in the times 2. It flows to a conformal field theory in the infrared. Again, the conformal field theory in the infrared has been studied in holography. There are solutions interpolating between ADS7 and ADS3 times S2 times S2. The central charges be computed by people, compared with holography. Here you using this formula, you can take the egg temperature limit. Again, you discover, and this time, curiously, even with the accurate coefficient, could be a mistake, but precisely 1/12 is the Carby formula. You get precisely, again, the Carby formula. And this function is either non-trivial as a function of the magnetic charge and the chemical potential that you can write using C extremization, and you get precisely this result. So, sorry, I'm late, let me go to conclusion. The main message of the talk is that there is still some interesting physics in this topologically twisted index in various dimensions. So, as I was mentioning, it would be interesting to get this family of black holes in ADS6. We're also interested to look at the dualities and how the index transform and the dualities. And a general comment is that I always discuss in this talk black holes with magnetic charges. As Shiraz knows very well, there is another set of black holes that still, after 10 years, wait for an explanation. The original, the most famous one, are class of rotating black hole, electrically charged rotating black hole in ADS5. There is another in ADS5. The problem is still open, and the problem is that in this case there is a large cancellation. So the natural object to compute is the superconformal index. Shiraz computed more than 10 years ago, goes like 1, as it should, cannot reproduce that. So my trick of the topological twist requires magnetic charge. Whenever you have magnetic charge, probably simplify and you can do some computation. And also there are many things that you can do in ADS4. People have started investigating one over correction. There is localization in supergravity. If you want, there is a huge literature about asymptotically flat black holes with precision tests and so on. This story about ADS it just started. It's much more complicated.
So this difference with the electric black hole from the boundary theory, this is just the issue of Landau levels, right? Is that what makes?
No, in the boundary, yes.
That is what makes the
difference that
very different.
So for the rotating charged black hole are just an ensemble of states in, say, n equal 4 superior base with given charge and angular momentum. So you need to count the state in n equal 4.
Yeah.
There is no deformation.
That's what I'm saying. It's the issue of the Landau level.
The deformation, induce the Landau level. For some reason, it's not obvious to me why it happens. For some reason, it helps the computation and it gives something that scales like n to the 3 over 2. Here, I don't know what to say. The only thing I can say is that if you take just the formula for the entropy of this black hole, there is a nice way of rewriting everything in terms of the Lajan form of something that has a simple form. It's written in terms of the Tufte anomaly of the field theory. So there is a simple way of repackaging this horribly written entropy in a nice thing that could have a field theory interpretation. But more than that, I can do.
Further questions?
Very briefly. In the case of the three-dimensional black hole, three field theory dimensional, four dimensional black hole, you have this sum over magnetic fluxes and integrand. Was the M dependence of the integrand just the x to the power kn?
Yes.
Nothing else, no other factor?
No, there is also a factor in the chiral field. So let me show you. Oops. This one, and also this one. Each chiral field depends on the flux, because there are Landau level, so each field that is charged under the gauge field feels the magnetic flux.
Thank you.
Yes, otherwise if you just have this, the sum of m would be very trivial, 1 over x to the k equal, so this beta equation would be x to the k equal 1, which is very simple, would be nice to do. Is the case that corresponds to pure Chern-Simons. If you apply this formula to pure Chern-Simons, you do the summation, you get the step in the formula, essentially. And these are the beta roots are x to the k equal 1. But with matter, it's a complicated beta answer system. These are the systems that appears in the integrability business. Nel caso scelto di visto.
This wonder mode element also changes when you change magnetic flux.
Say it again?
The wonder mode portion also has magnetic charge.
Not in
your case it's not there.
Not in many cases. So if there is an extra parameter that you can introduce it, which is conjugated to the rotation of the black hole in 4D. You can add rotations, more complicated. It's a sort of amp omega background. So there is an extra parameter that you can introduce, so you can do the equivariant formulation of this. In that case, the Vandermonde would be modified by factor of error, but in this case, it's not.
If it were true that the Vandermonde actually depends on the magnetic flux and you have to sum over, do you have an idea of summing it, including those vectors?
No, this case of the rotating black hole is still open in the sense that there are no black holes in the literature, so there is no urgency of checking something. But I think Risto, Chiaratore, and someone else finally found it. So soon there will be a formula. I had a preview of this formula, but this trick of resumming is not working also because you need to in this equivariant version, you need to replace the rational function with a cupocam. And resumming is a mess. There are other formulas along this line that has been written by Closet, Will, and Kim as a series of papers where they generalize this story of the critical potential to all possible partition functions in 3D. So they always claim that there is a formula of this form here. Okay? And in principle, using the expression, one should be able to do this. But it's not simply something.
Okay, we can take a break. Let's thank Alberto again. And meet again in 15 minutes.